Hey, everybody on YouTube. I want to give an overview of what some of the things we'll be learning in this class. So this is an introduction to abstract algebra, which means we'll be learning about groups as one of our main topics. So let me show you this CD cover as one example of a group. Okay, so pretend we fix this outline of where the square is. And then I consider all the different symmetries of this square. All right, so I could rotate the square by 90 degrees, or I could rotate the square by 180 degrees, or I could rotate the square by 270 degrees, which is the same as 90 degrees in the other direction. Okay, so those are four different symmetries of the square. They map the square to the same spot. Although we can see that it's been mapped in a certain way just by, tracking how the image is changed. Another symmetry of the square is these flips, right? So I could flip horizontally, I could flip vertically, I could flip across this diagonal, or I could flip across the other diagonal. And those are also symmetries of the square. Okay. So there are 8 symmetries of the square. First, let me tell you how not to think of the 8 symmetries. Okay. The way you should not think of these 8 symmetries is 1, 2, 3, 4, and then, oh, I guess on the back side, we have 1, 2, 3, 4. Okay, I don't want you to think of the symmetry as the ending position. I want you to think of the symmetry as the action that puts you in that position. Okay, so I want you to think of the symmetry as this rotation that ended here, or maybe this rotation. Okay, or maybe this horizontal flip. So think of a symmetry as an action. Okay, and the value of that is now I can compose symmetries. I could rotate 90 degrees and then do a horizontal flip. Let's try it. Rotate 90 degrees, then do a horizontal flip. Okay, where's the sun? It's on my top right. Okay, so let's do that again. I could rotate 90 degrees and then do a horizontal flip. Where's the sun? It's on the top right. Or I could do the horizontal flip and then rotate by 90 degrees. So do the horizontal flip and then rotate by 90 degrees. You'll notice the sun's in a different spot if I first do the horizontal flip and then 90 degrees compared to rotation by 90 degrees and then horizontal flip. Okay, so when you think of these symmetries as actions instead of positions, you can compose them. It makes no sense to combine this position with that position. You can't combine positions, but you can combine actions, a rotation versus a flip and then a flip, or for example, in the other order, a flip and then a rotation. So that's where the power of group theory comes in, is that you can compose symmetries, and we can identify what is a new symmetry we get. So let's go back to this 90 degrees rotation and then the flip. What symmetry was that? Okay, if I do the 90 degree rotation and then the flip, that's the symmetry that's the same as this flip. Do you see that? Okay, so rotating by 90 degrees and then the horizontal flip, that's the same as just starting here and doing a diagonal flip. Okay. Let's do them in the opposite order. What if I do the horizontal flip and then the 90 degrees? Okay, so horizontal flip and then 90 degrees. That's the same as just a single flip along the other diagonal. Okay. So we're now able to compose symmetries, compose 2 symmetries, and get a third, which is really cool. You can't compose a position with another position to get a third position. That makes no sense. So other objects have symmetries. So this cube has rotational symmetries. I think it has 24 rotational symmetries. And the way you could count that is, well, when I rotate this cube, there's 6 different places I could move the bottom. I could leave it on the bottom, or I could move the bottom to any of the 6 other faces. And then once I've told you where the bottom goes, this white part, then there's 4 different rotations with the bottom in that position. So I think there's 24 rotational symmetries of the cube, but what's not so important is the number of 24. What's more important is how you can compose symmetries. So you can do a 90-degree rotation up, and then you can do a 180-degree rotation around, and that gives you a new symmetry. Last thing I want to say is that those were finite groups of symmetries, but you could also have infinite groups of symmetries. So what's sort of the rotational group of symmetries of this frisbee? Well, you could rotate at any different angle you want. And again, you should think of this as an action. So I could take this 90-degree rotation and combine it with a 180-degree rotation. And when I combine those, I get a rotation of 90 plus 180 degrees to get me to 270 degrees. Okay. Um, Wonderful. So those are the basic objects of group theory. These groups of symmetries. We'll have groups that arise from very symmetric objects, but we'll also have groups that just arise more algebraically. But groups are important in the real world. They're the language of so many things that go on in the real world. Um, they're valuable in cryptography. So how you send your credit card to Amazon without Amazon knowing, or without an interceptor knowing your credit card. Group theory is important in coding theory. So how we transport signals from a spaceship back to Earth without it getting corrupted. And group theory is important, as one of our students pointed out yesterday, in quantum physics. So group theory is the language of quantum physics as well. Any public questions? All right.